Hello, hi, welcome back. So, if you remember from the last video, we made a raycaster. However, it was unacceptably slow. Even on 320 by 240, we were getting 34 frames per second. So what we're looking at here is a bunch of methods that I tried to optimize the code. First thing I did is I went through the variables, and if we look at the code for rendering, then what we're doing is we're creating a bunch of like local variables in the method, and I said, okay, well, let's declare those as class member variables, and so Python isn't allocating a bunch like blocks of memory repeatedly if those blocks of memory don't need to be reallocated. That made like 1 frame per second difference, on average about the same. Then I said, okay, let's take all of the ray information and abstract that out into a ray class, and we'll say that the engine has an instance of the ray class which it reuses. And that slowed things down a little bit, because it meant we were calling more functions in our draw call. Every time we call a function, the state of the registers is saved, and everything is kind of saved onto the function call stack. So there's a little bit of overhead there. However, that did have the benefit of making the code more readable and more engineerable. Is that a word? And then I had the big one. So you can imagine that repeatedly calling an OpenGL draw call for every line of a wall segment is just pointlessly expensive. It would be much better to do some work to find out the left side of a wall and the right side of a wall, and then draw that segment all as one draw call. Actually, if we had access to low-level memory, it would be just as efficient to write the memory segments of a single buffer for the whole screen with like a memory copy sort of operation, and then just pop that screen over as a whole texture. We don't have that. We could kind of fake it, but it's probably not efficient. So this line lumping method is the big one. So let's jump in and have a look at how we would make something like this. So to start with, we'll grab everything that we had before, copy that, make a folder, call it optimized. So we're going to be modifying this a little bit. Then let's open this up. Let's start with the shaders. So what I want to do is I want to draw not a line, but a segment. And so this fragment shader doesn't have to change. It's the vertex shader. So instead of passing in the position of the line as a dynamic bit of information, I'm actually going to, in my code, calculate the position of the segment and then send that in. So I won't need to make any extra transformations on this. So see that this is almost like the simplest shader that you can make. We just do nothing, just set a vertex position and then set a color. That's it. Okay, so let's look back at this code. Now we've got the player, and yep, this all looks good. That doesn't have to change. The game board I don't think has to change either. Just quickly checking this against my code. Yeah, this is fine. This is acceptable. Okay, what I am going to do is I'm going to work in the view classes. So I'm going to make a class called array, and that will have all the information for performing the DDA algorithm. for tracing the ray. And then I'm going to have a class called a render state, because when the ray hits a wall, we want to save a bunch of information. We want to save the x position of the line along the screen from left to right. We want to save the scale factor, basically tracking how far away the wall was, as well as the side of the wall, whether it was horizontal or vertical, and the position of the wall on the map. Because let's look at our game board. So we have a bunch of numbers here, and say this number here represents a block, but this block is made of a bunch of rays. So to start with, we'll say the player is here and they shoot a bunch of rays. A number of rays will be hitting the same block. And what we want to say is for every ray that hits the same block, store that up and then draw that as one segment, if that makes sense. So we want to know where on the map we hit the board. Okay, but there's actually a bunch of tweaking which we have to do with the engine first, just to set things up. So just checking here. Okay, so for the vertices, instead of drawing a single line, we now want to draw a rectangle, basically a quadrilateral. So I'm just going to pass this in. There's actually no need to do this, but why not? So 3 positions represent a point, and then 3 points represent a triangle, and then our rectangle, our quadrilateral, will be 2 triangles. So I'm just kind of reserving that in that data space. Again, not necessary, but why not? Okay. Yeah, this looks fine. We've set this up. Self.colors, that's great. Now I'm going to make a function called Initialize view variables. And what this function does is it just sets up a bunch of local variables which are used later on in the ray tracing. Sorry, raycasting. Okay. So I'm going to copy this in. Yeah, get rid of that. Okay, so a lot of this should make sense. We have the forwards direction, the right direction. So instead of declaring that variable anew, we will just be updating it with new information. Okay. Interpolation coefficient, again, is tracking left to right. Distance to camera, that's fine, that's all normal. We probably don't need this, right, because we're not passing in a model transform anymore. Now, last drawn x. What this variable tracks is the rightmost position along the screen where a sector was last drawn. Why are we doing that? Well, for instance, let's say we are drawing a bunch of walls, but there's a wall just to our right where the beginning point we can see, but we can't see the end point. It's out of view. So we just want to keep track of where we have drawn up to, because we might have to just finish off the rest outside of the loop, if that makes sense. Okay, so that is done. Now, of course, we're going to have to update our draw scene function. But before we get to that, I want to just kind of do this all in one thing. So I want to start setting up the ray and the render state. I guess let's start with the render state. It's a little smaller. Okay, so the render state. Yeah. Okay, I'm just gonna paste this in. Okay, so some information that we need. And by the way, what I'm doing here is with this 0.0, I'm saying this variable is probably going to be a floating point number. Python can change variable types on the fly, but there is some overhead in that. So this is just, I'm just hoping that Python will allocate this as a floating point number and then update it, not change its type. Okay, so we have the X position along the left and right of the screen where the hit was made, where it will be visible. The scale is, how big the thing should be. The type of side which was hit, the map coordinate where the hit was made, and then this self-complete is just tracking whether, because we're going to have a bunch of these tracked by the engine, just tracking whether the hit has been updated, because we're going to be reusing this data. So if I go back to the initializer, yep, a lot of stuff here. Then I want to track two things, or three things actually. So I want to create a render state to track the left side of a wall that I see. I want to create a render state for the right wall that I see, and then I'm going to need a third render state because once the left side is hit, then we're going to progressively scan, and if the next ray that we see matches the type of the ray that the render state which we had for the left, then we just keep going, update the render state B, and then keep going. Otherwise, we update render state C if we see something unusual, and then we draw between A and B, and then we copy C into A. So this is just a temporary variable to keep things moving clearly. And while we're at it, let's do this. Let's set up a ray variable. Okay, and that's all the information we need in the render state class. So let's go to the ray class and have a look at that. Okay, so what is a ray? Really, wrong one. Really, a ray is a position and direction, as well as a procedure on how to step. It implements the DDA algorithm. So when we create this is tabbed over wrong. We initialize the position, the direction, the map coordinate, all of this stuff. This is just taking the variables from the draw scene stuff down below. Okay. Now, I'm not initializing this with arguments because we're just going to have one persistent object which is updated. So the next function I want to write is something to set things up. So I'm going to call this the Orient Function. just copy this in. Okay, so we take a position and direction. We save that information into our variables. We get our map position. This is really just the same as before, right? We just set up our delta distance and our side distance and our step x. This is really the same code as before. So we can go back down to our engine, and then down here. Actually, you know what? I'm just going to populate all of this and then I'll clean it up later. Okay. So the next thing is I'm going to have a function called step. So Orient sets up all the parameters which are needed, and then step will be called repeatedly to step the ray forward one step at a time. So here's our step function. And again, this is really just doing the same as down below. Just abstract it out into a separate class. So now we can get rid of that. And we can start working on our draw scene function. Okay, let me just double check this. Okay, so we don't need position because this is not used anywhere other than the ray, so we can hide that for now. This is fine, we get the forwards in the right direction. Okay, now I'm going to set up a few other variables. Okay, we always reset the last drawn x to the left-hand side of the screen. And we set our left side x coordinate to negative 1.0, and we reset the render states. Okay, that's fine. Now let's set up our ray. So we take our self.ray and we orient that. Now I'll use that variable before that I got rid of. Okay, and then for position, direction, sorry. For that, I'll use this stuff. There we go. Okay. And we don't need this. That is done within the ray class. We also... yeah, we don't need all of this. Okay, let me go. Doesn't make a difference, but makes it a little more readable. Okay, so what is this? This is really the ray step method. self.ray.step takes care of that. And then when I goof this up a little bit, this should be self.hit because we're saving this as a member variable. Okay. Right, so now I'll set this up. Okay, I'm actually going to get rid of all of this stuff. We don't need it. Okay, that's a fair bit cleaner. So we trace along until we hit something. When we hit something, we calculate our distance that we need to draw it. Okay, so let me just check where I am here. Okay, so we've hit something. The first thing we want to check is sector A, is render state A complete, or do we need to fill it in? So we say if, actually no, I won't do that. Okay. Okay, so I'm going to make a function called Populate render state. There's nothing special about this function. It's just to avoid, because populating the render state involves copying over about 3 variables, and if we do this a number of times, this saves a bit of writing. Okay, so I'll just copy this in. Okay, so presumably the ray has hit something. What am I doing here? Presumably the ray has hit something valid, and so we have valid information. So what we can do is we can just copy in the ray's map position, the side that it hit, and calculate the scale just using the reciprocal function, just like we used before. Now note that we're not setting the x value, even though we could. And the reason for that is that I want to have a little bit more control over the x values so that I can stitch the line segments together. I was doing this before and it worked, but there was a gap between the line segments, so I'm just being extra careful there. Okay, so where were we? Okay, so we populate the render state. The x coordinate of hit A has already been set at the start. We set it to -1.0, the left side of the screen. So that's fine. But what we will need to do is we will set up some variables in hit B. What do we want? I want to set the side equal to the current side. And what this is doing is it is telling it's telling the render state B what to expect from the next ray. So we set it up to have the same kind of state information as, or not state information, but like hit description, like the same, like horizontal or vertical side at this map coordinate. So then in the next step, if the next ray does not match that, well then, yeah, we can draw the whole segment. Okay, let me see. Okay, good. Otherwise, and I'm going to paste this in. So now we've got a ray that's hit something and we are not filling in segment A. This means we're deciding whether to draw a new segment or not. Our test for this is a number of conditions. Either our side is different, so we've switched from a horizontal to a vertical side, or we've switched to a different y coordinate, or we've switched to a different x coordinate. In all of those cases, we want to stop and draw a new segment. So we say, okay, hit B is complete. Now stitch together hit B and hit C, get them to the same x coordinate, and then take the ray information, and this ray information has missed, segment B, so stick it into segment C. Okay, otherwise we are good, and just take the ray information and throw it into segment B. And just because I'm paranoid, I'm always updating the x coordinate at every stage. Okay. So then what do we do? Well, if we have a complete, hit A and hit B, then we can go ahead and draw that segment. So I'm going to make a function called drawSegment. It takes in the argument, a color as an argument. Let's go ahead and make that function. Okay. I'll just paste this in, why not? Alrighty. Sorry. All right, so we flag we flag piece B as incomplete because it's been drawn. We update the last x coordinate that we've drawn up to. Now we do the work of passing in a new set of vertices to draw a quadrilateral. So if we kind of label these, I'll label this point 0. Then point 1. So point 0 is on the right at the top. Then we go counterclockwise to point 1, on the left on the top, and then point 2 on the left on the bottom. So that makes one triangle. Then we copy point 2 again. So on the left on the bottom, on the right on the bottom, and then on the right on the top. So that's a copy of point 0 again. Okay. That's it. All right. So then we do the work of passing in that data. So we bind this in, get a memory handle to it, and then we use memmove to move all of that data in. And then we unmap the buffer, okay, and then we pass in the color as a uniform. And this bit here essentially does the drawing. Okay, then what we do is we update hit A to take the information that we were storing in hit C. And we stitch everything together. So, I mean, we kind of did this already, but again, I'm being paranoid. And then we just copy all that. Yeah, so again, what this is doing is this is populating hit B to tell it what to expect from the next ray, just like we did right back above. No, not here. Up here. So we populated ray A, and then we pre-filled ray B. Okay, so that's cool. We've got that. It all seems to be working. Okay, now the next step is we just want to do our kind of catch-all draw. So that is just double checking. So what we're saying is finally, outside of the while loop, if we finish everything, but we have not drawn up to the end of the screen, and we do have a valid, like, hit A, then we'll just set up hit B with all the information that we have right now, and then just draw all the way across. Okay. So hopefully that's working. I think that's everything. We'll just give it a shot. Oh, yeah. Okay. Why is that not working? Must have just been a spelling error. Yeah, let me just. All right, Initialize. Huh. You got me. You got me, Python. Engine object has no. Yep, of course. There we go. Now, as you can see, this is going quite a bit faster than 300 frames per second. It's also not working. It's not a good sign. Maybe this helps. We'll see. So if I go down to and I'll start limiting the frame rate to 60 frames per second just so the thing is playable. Right, so what I've done is I'm just resetting the scales to 0 so that if I have any stray render states where the scales haven't been set, they will just not be visible. Why are you doing this? This is bad. This is bad, but there's probably just some typo that I've missed somewhere, so I'll just paste in the code that I had before from my working version. It's probably something like I had some local variables that I forgot to switch to like self.variable. We'll see if this works. There we have it. Okay. So there, it works. It works pretty well. Let's uncap the frame rate and check how it's going. Cool. Not bad, not bad at all. Okay, so there is one more optimization we can make. And that is maybe instead of, let me just go back to the map. Maybe instead of drawing a sector for every block, if we get a bunch of blocks all together, then draw that as one sector. That would be even better. So this is starting to use, I think it's called Coherence Optimization. It's the idea that if we hit something, the thing next to it should have the same sort of property. So that's actually not too hard to implement now. We just have to make another function in our engine. Which I'm going to call new segment. And what we're doing is we take a render state, an array, and we test whether that should begin a new segment. So this is actually taking this code here and just making it simpler, or extending it. Okay, yeah, so I'm gonna just put that in. So, first thing we do, if we've changed from a horizontal to a vertical wall or something, then there's nothing we can do. That is a new segment automatically. But if this doesn't hit, then the two rays are hitting the same type of wall. Now, if they're hitting a vertical line, then, well, we can read it here. We check to see if the next line that we're hitting is above or below, but at the same horizontal position. So our horizontal check is whether the x coordinates are different. If that's true, then yes, we're in a new segment. Our vertical check is whether the vertical distance is bigger than 1. If that's true, then yeah, we're in a new segment. And it's the same sort of thing down below. So now what we can do is we can take that and use it. So here we are saying if we're in a new segment based on our render state hit B, comparing that to our ray. Self.ray. Then we go ahead and do that. So as you can see, yes, it's still incredibly fast, but the most complicated scene was something like this. Before, this was running at about 80 frames per second. Now it's running at about 100 and something. That's the hardest part of this scene. So we've improved the worst case. And yeah, the best case is still incredibly fast. If I look at something like this, it's drawing all of this as one segment, which, as you can see, is incredibly fast. So that's good. 200 frames per second for this is still not insanely fast, and that comes down to language differences. That's fine. So what was I going to do? Well, we can also, now that we've sped it up, we can increase the resolution. And that makes it slightly better. It's still a little bit janky with anti-aliasing on the tops and bottoms here, but I would say that's acceptable for what we're doing here. Okay, so hope you had fun, and yeah, I don't know, see what we do next time. See you next time. Bye.